Hello and welcome back. If you're here for the first time, I'm so glad you found your way. And if you've been here before, then you already know what this is. A quiet place at the end of a long day, where the universe opens up just enough to let your mind wander somewhere beautiful before it drifts off to sleep. Tonight, we're going somewhere vast, somewhere ancient, somewhere that's been turning slowly, in the dark, for over 13 billion years, long before there were eyes to see it, long before there was anyone to wonder about it at all. Tonight, we're going home, not to the house or the apartment or the room you're lying in right now, but to the larger home, the one that contains everything you've ever known, every star you've ever wished upon, every night sky you've ever stood beneath in silence. We're going to the Milky Way. Over the next little while, I'll share with you 100 things about our galaxy. Truths, mysteries, wonders, and quiet impossibilities that live right above our heads every single night. Some of these facts will be familiar, like a name you half remember from a dream. Others will surprise you. A few of them might even change the way you see the sky. And all of them, I promise, are best experienced with the lights low, your body warm, and your breath just a little slower than it was an hour ago. So find a comfortable position. Let your shoulders drop, let your jaw unclench. And let's begin. The Milky Way is old. Not old the way a building is old, or even old the way a mountain is old. The Milky Way began forming less than 1 billion years after the Big Bang, which means it has been quietly turning in the dark for roughly 13 billion years. Think about that for a moment. 13 billion years. The Earth itself has only existed for about 4.5 billion of those years, which means that for the first 8.5 billion years of the Milky Way's life, our planet simply did not exist. There was no ground to stand on, no ocean to sail, no sky to look up at. The galaxy was already ancient by the time the sun ignited for the first time, and yet here we are, late arrivals in a story that began long, long before us. But here is something that might gently shift the way you're thinking right now. You are made of this galaxy, not just living inside it, not just orbiting within it. The atoms of your body, the iron in your blood, the calcium in your bones, the carbon woven through every cell, were forged inside stars. Stars that lived and died billions of years before the Earth existed. Stars that exploded their guts into space, scattered their material across thousands of light years, and eventually seeded the clouds that collapsed into our sun and our world. The galaxy didn't just make stars, it made you. Now let me ask you something, because I think it will help you settle in. Have you ever looked at the night sky on a truly dark night, far from cities, far from streetlights, and felt, even briefly, like something was looking back? That feeling isn't irrational. It isn't poetic exaggeration, because, as you're about to discover, the Milky Way is not a static backdrop. It is alive with motion, with history, with violence, with patience, and with a kind of slow, enormous creativity that takes billions of years to complete a single thought. Let's spend the night exploring it. Our galaxy contains somewhere between 100 billion and 400 billion stars. The range itself tells you something important. Even counting the stars in our own galaxy is something we haven't fully figured out. We can't photograph it from above. We can't fly outside and look back. We are sitting in the middle of the Milky Way, like a person trying to describe a cathedral from inside its walls, unable to see the full shape of the building they're standing in. The estimates come from measuring brightness, density, and extrapolating outward. But the truth is, we are still learning to count our own home, and the stars we can see with the naked eye, on the clearest, darkest night imaginable, represent roughly a few thousand of those 100 billion to 400 billion suns. You could stand in a field in the middle of nowhere, tilt your head back, and look at every single point of light you're capable of seeing, and you would be seeing approximately 0.00003% of the Milky Way's stellar population. Not even the surface of the ocean, more like a single drop of seawater cupped in your hand. Have you ever wondered why the Milky Way looks like a streak of pale light across the sky, rather than a glowing disk you could see in full? The answer is simple and a little dizzying. You're inside it. When you look at the smeared band of light that crosses the night sky, you are looking along the flat plane of the galaxy's disk, peering through billions of overlapping stars the way you'd look down a long corridor and see the walls and ceiling blur together in the distance. The Milky Way doesn't look like a spiral from Earth because we're embedded in the spiral itself. We're like fish trying to describe the shape of the ocean. Now, stay with me here, because this next part is one of my favorites. Our solar system, the Sun, the Earth, every planet, every moon, every asteroid and comet in our neighborhood, is orbiting the center of the Milky Way. Right now, as you lie there, as you breathe, as your eyes grow heavy, we are moving. The solar system travels at roughly 828, soon kilometers per hour through space. That's about 230 kilometers every single second. And still it takes approximately 225 to 250 million years to complete one full orbit around the galactic center. This journey is called a galactic year. In all of the 4.6 billion years the Sun has existed, it has completed this enormous loop fewer than 25 times, 25 galactic years. We think of the Earth as ancient, and it is. But on a galactic timescale, it's still relatively new. The last time the solar system was in the section of its orbit it currently occupies, the supercontinent Pangaea had only just begun to break apart. The first dinosaurs were just appearing, and the time before that, 2 galactic years ago, the first complex animals were evolving in the seas of a young Earth. The galaxy is not counting in years, it's counting in eons. Now here's something that might make your mind do a quiet somersault. What if I told you that some of the stars in the Milky Way are older than the Milky Way itself? It sounds impossible, and yet it's true. Scattered throughout the galaxy's outer halo, that vast, diffuse sphere of stars and dark matter that surrounds the flat disk, there are ancient stars with almost no heavy elements in their composition. No iron, no calcium, almost nothing beyond hydrogen and helium. This chemical signature marks them as some of the very first stars ever born in the universe. They did not form inside the Milky Way as we know it. They formed in tiny, primordial galaxies that existed long before our own, galaxies that eventually collided with and were absorbed by the proto-Milky Way billions of years ago. These stars are essentially refugees from an older universe, wandering in the halo of our own galaxy, carrying light from a time we can barely imagine. And speaking of wandering, let me ask you something. What do you think it would mean for a star to be rogue? Not a rogue planet or a rogue asteroid, a rogue star. A full-blown, hydrogen-fusing, light-emitting star, hurtling through intergalactic space with no galaxy to call home, no stellar neighborhood around it, just emptiness in every direction for millions of light years. Does that sound like the beginning of a science fiction story? Because it's not. It's real. These are called hypervelocity stars, and they are among the strangest objects we've found, drifting beyond the spiral arms. Here's how they happen. Near the center of the Milky Way, there is a supermassive black hole. We'll return to it in detail soon, and sometimes a pair of stars ventures too close. In the chaos of the encounter, one star is captured, spiraling inward toward its doom, but the other star is slingshot outward with such extraordinary force that it achieves escape velocity, leaving the galaxy entirely. It travels alone. At more than 1,000,000 kilometers per hour, it crosses the outer edge of the Milky Way and flies into the dark between galaxies. It will never return. It will never find another home. It is a star, burning faithfully, lighting nothing but the void. These rogue stars are the galaxy's exiles. And if there were a planet orbiting one, though that itself is unlikely, the night sky from that world would show nothing but darkness. No neighbor stars, no galactic band of light, just an utterly black and empty cosmos, lit only by the glow of the star they orbit. Imagine that. Imagine growing up under a sky with no Milky Way, no constellations, no sense of belonging to something larger, the exile star and its hypothetical world, utterly alone. Now let's drift inward. Let's move toward the center of the galaxy, because that is where things get strange and magnificent, and, if we're honest, a little frightening. At the very heart of the Milky Way, hidden behind curtains of gas and dust so thick that no visible light can penetrate them, lies an object called Sagittarius A star. It is a supermassive black hole, and when I say supermassive, I mean that almost casually because the actual scale of it is the kind of thing that resists being held in the mind. Sagittarius A star contains a mass equivalent to more than 4 million suns. 4 million suns, compressed into a region of space smaller than the orbit of Mercury around our own sun. We cannot see it directly. Black holes, by definition, do not emit light, but we can see the effect it has on everything around it. Stars near the center of the galaxy, stars that are otherwise completely normal, have been observed completing full orbits around the central black hole in as little as 12 years. 12 years. Those stars are moving so fast, under such incredible gravitational pressure, that they complete an entire orbit in the time it might take a child to go from kindergarten to high school graduation. And the thing pulling them around it is invisible. But here is what keeps the story interesting. And please stay awake just a little longer for this one, because it's worth it. Sagittarius A star is, by the standards of supermassive black holes, remarkably quiet. It is not currently consuming large amounts of material. It is not actively flaring or blazing. If you could somehow observe the Milky Way from a distant galaxy, our core would look dark and subdued compared to galaxies with active nuclei. But there is strong evidence that this was not always the case. The Fermi bubbles, two enormous lobes of high-energy gamma-ray light extending tens of thousands of light-years above and below the galactic center, are almost certainly the echoes of a past outburst. Something enormous happened at the core of our galaxy, perhaps 2 to 4 million years ago. Some scientists believe the central black hole briefly ignited as a quasar, one of the most luminous objects in the universe, devouring gas and radiating energy visible across millions of light years. If that happened, our galaxy would have looked very different from the outside. A brilliant, burning heart in the center of a spiral arm. That time has passed. What remains are the Fermi bubbles, ghostly monuments to an ancient fire, invisible to the naked eye, but glowing with the residue of an explosion that happened before our earliest human ancestors walked the earth. Are you still with me? Good. Then let me ask you something a little quieter, a little more personal. Have you ever looked up at the sky and wondered how many of those stars have worlds around them? How many of those tiny specks of light are actually suns, like ours, with planets orbiting them, with moons, with maybe, somewhere, a surface where something has learned to wonder about its own sky? because here is what we know now. Planetary systems are not rare, they are the default. Almost every star we study carefully turns out to have something orbiting it. Some have gas giants the size of Jupiter, others have rocky planets smaller than Earth. Some are wrapped in dozens of moons, others orbit in pairs caught in gravitational dances around binary suns. Across the Milky Way, the number of planets likely runs into the trillions. Trillions, and many of these planets sit within what astronomers call the habitable zone. Not too hot, not too cold for liquid water on the surface. Water, which seems to be one of life's most persistent prerequisites. We have not yet found life elsewhere, but the math of the galaxy makes the question feel increasingly less like fantasy. And the Milky Way itself has something like a habitable zone too. Not for individual planets, but for the galaxy as a whole. The inner regions of the galaxy, packed with stars, bathed in radiation from the active core, swept by frequent supernova explosions, are harsh places. The outer edges of the disk, too far from the center for the chemistry of heavy elements to accumulate, are spare and cold. But in between, there's a wide band sometimes called the galactic habitable zone, where star density is moderate, where radiation storms are less common, where the elements necessary for complex chemistry, carbon, oxygen, nitrogen, iron, are plentiful enough to build living things, and our sun, your sun, sits comfortably in this zone. We are not too close to the chaos of the core and not too far from the richness of the center. We're in exactly the right neighborhood. Does it feel like we were placed here on purpose? That's the kind of question that keeps people awake at night. But the quieter, stranger answer is that the galaxy did not need to place us here intentionally. It just needed time, and it had 13 billion years. Now, do you know what dark matter is? You've probably heard the term. But do you have a sense of what it actually means to say that most of the Milky Way is made of something we cannot detect, cannot see, cannot measure directly, and cannot yet explain? Here is the situation. When astronomers look at how stars orbit the center of our galaxy, they expect the same behavior we see in our solar system. Planets farther from the Sun orbit more slowly than planets closer in because they experience less gravitational pull. If the Milky Way worked the same way, stars in the outer disk should orbit more slowly than stars near the center. But they don't. Stars in the outer regions orbit almost as quickly as those near the middle. This is mathematically wrong, given the mass we can see. The galaxy should be flying apart. The visible matter, all the stars, all the gas, all the dust, is not nearly enough to hold it together at those speeds, and yet it holds. The only explanation that fits the data is that there is an enormous amount of additional mass that we simply cannot see. This unseen substance, dark matter, is estimated to make up roughly 85% of the Milky Way's total mass. Not 5%, not 30%, 85. The galaxy we see, the beautiful spiral of glowing stars and luminous gas, is essentially a thin veneer floating on top of an enormous dark structure we can't directly observe. The Milky Way's true shape is not defined by its stars, it's defined by dark matter, and we do not know what dark matter is. We've been looking for decades. We've built detectors buried miles underground to catch dark matter particles. We've built particle accelerators, hoping to produce them. So far, nothing. The answer is out there, somewhere, in the dark. Here is a gentler mystery, a softer one. Before we go a little further, you know how the Milky Way looks in photographs. That magnificent, sweeping spiral, like a giant pinwheel of stars. Here's what those photographs don't show. The Milky Way is warped. It's not flat. The outer edges of the galactic disk bend upward on one side and downward on the other, like a vinyl record left in the sun, or a wave moving across the surface of a spinning disk. The warp is subtle. You wouldn't notice it if you were standing on a star in the outer regions, but it's real, and astronomers only discovered its full extent when they mapped hydrogen gas far beyond the visible stars using radio telescopes. The leading explanation is that the Large and Small Magellanic Clouds, two satellite galaxies orbiting the Milky Way, are gravitationally tugging on its edges, bending the disk as they pass. A pair of dwarf galaxies, millions of light years smaller than our own, gently warping the shape of our home. And the Magellanic Clouds themselves have a story worth telling. For a long time, astronomers assumed they were long-standing companions of the Milky Way, galaxies that had been orbiting us for billions of years in comfortable, familiar loops. But new measurements of their velocities suggest something remarkable. They may be moving too fast to be gravitationally bound to the Milky Way in the traditional sense. They might be visitors, strangers passing through on their first close approach to our galaxy, pulled in from the larger cosmic web by gravity and currently making their nearest pass before being either captured or flung away. If this is true, it means the Magellanic Clouds are not old friends. They're newcomers, and they've already left a mark. Not just the warp in the disk, but the Magellanic Stream, a vast ribbon of hydrogen gas hundreds of thousands of light years long, trailing behind them across the sky like a tail, stripped away by tidal forces. This stream will eventually fall into the Milky Way, adding fresh gas that may fuel a new generation of star formation. Even a passing encounter has consequences that last for billions of years. Can I tell you something about star formation? Because it's one of the most quietly beautiful processes in the galaxy, and I think it deserves a slow, careful telling. Stars are not born from nothing. They are born from cold, dark clouds of hydrogen gas that drift through the galaxy's spiral arms. Clouds so enormous they would dwarf any structure you've ever imagined. Some of these molecular clouds span hundreds of light years across. They are, in the visible light we're accustomed to, essentially invisible. They look like holes in the starfield, dark patches where the distant stars are blotted out by the cloud's dense interior. But in infrared and radio wavelengths, they glow with complex chemistry: water, ammonia, carbon monoxide, and even organic molecules like simple sugars and alcohols, the chemical precursors to biology. Within these clouds, something begins. Maybe a shockwave from a nearby supernova nudges a region of the cloud slightly denser than its surroundings. Maybe the slow sweep of a spiral arm compresses the gas. Whatever the trigger, gravity begins to take hold. A small region starts to collapse. As it falls inward, it heats. It spins faster, the way a figure skater pulls their arms in to speed up. The collapsing cloud flattens into a disk, a swirling protoplanetary disk, with a dense, glowing core at its center. That core, as it grows denser and hotter, eventually reaches the critical pressure and temperature for hydrogen fusion to ignite. And in that moment, a star is born, a star, from nothing but cold gas and gravity and time. And as it blazes to life, the remaining material in the disk around it, the gas and dust that didn't fall into the star itself, begins to clump and coalesce. Small particles stick together. Clumps become pebbles, pebbles become boulders, boulders become planetesimals, and over millions of years, gravity organizes all of this into planets, moons, asteroid belts, comets, an entire solar system assembled from the leftovers of a star's birth. It happened here, 4.6 billion years ago, around a middling yellow star in the Orion spur of the Milky Way. This exact process played out, and here you are. Now let me ask you something. that might keep your mind moving gently for another few minutes. When a massive star, something 20 or 30 times the mass of the Sun, reaches the end of its life, what do you imagine happens? A gradual fading? A quiet dimming? No. What happens is one of the most violent events in the observable universe. The star exhausts its nuclear fuel. The core, which spent millions of years fusing lighter elements into heavier ones, has built up a core of iron. And iron is the end of the road for stellar fusion. It takes more energy to fuse iron than the reaction releases, so the fusion stops. Suddenly, the outward pressure that held the star against gravity's inward pull vanishes, and the star collapses in less than a second. A core the size of Earth is compressed to the size of a city, roughly 20 kilometers across. The density becomes so extreme that protons and electrons are forced together to form neutrons. This is a neutron star, and the outer layers of the massive star, collapsing inward and then rebounding off the suddenly incompressibly dense core, explode outward in a supernova, an event so bright it can outshine an entire galaxy for weeks. The energy released in a few seconds is comparable to what the Sun will emit across its entire 10 billion-year lifetime. The shockwave expands outward at thousands of kilometers per second, crashing into the surrounding interstellar medium, compressing nearby gas clouds, triggering new rounds of star formation, and scattering the heavy elements forged in the dying star's core. Silicon, iron, nickel, gold, platinum, uranium. Across light years of space, these elements will eventually be incorporated into new stars, new planets, new living things. The supernova is not just an ending. It is the galaxy's most dramatic act of recycling, the way the Milky Way converts one generation of stars into the raw material for the next. And something remarkable happens when two neutron stars, those ultra-dense city-sized remnants of dead massive stars, spiral together and collide. This event, called a kilonova, is even more exotic than a supernova. In the final fractions of a second of the merger, the conditions of extreme temperature and density forge enormous quantities of the heaviest elements: gold, platinum, iridium, and more. The kilonova sprays these materials into space in a spray of radioactive light. Every atom of gold on Earth, every wedding ring, every piece of jewelry, every gold coin, was forged in the collision of neutron stars, not in the Sun, not in the Earth's mantle, in the death spiral of two compact stellar remnants that lived and merged billions of years before our solar system existed. You are wearing the wreckage of ancient catastrophes. Let your breath slow for a moment. We're about halfway through, and there's so much more to explore. Did you know that the Milky Way is currently in the process of eating another galaxy? Not metaphorically, literally. The Sagittarius dwarf spheroidal galaxy, a small, faint companion galaxy, is being torn apart by the Milky Way's tidal forces right now at this moment as you lie in your bed. Its stars are being stripped away in long, looping streams that wrap around the galactic disk multiple times. Some of the stars that you see in the night sky, ordinary-looking stars scattered across the halo, are Sagittarius dwarf stars, ripped from their home galaxy and absorbed into ours. Astronomers have mapped several of these tidal streams, tracing the ghost of the Sagittarius dwarf across the sky. In 1 billion or so years, nothing recognizable will remain of it. The Milky Way will have consumed it entirely, and its stars will simply be Milky Way stars, their origins forgotten. And the Milky Way has done this many times before. One of the most significant such mergers, called the Gaia Sausage or Gaia Enceladus merger, happened roughly 8 to 10 billion years ago, when a dwarf galaxy, roughly a quarter of the Milky Way's mass, spiraled inward and collided with our young galaxy. The merger was enormous by cosmic standards. It likely triggered massive waves of star formation. It scattered new stars throughout the halo. It may have helped shape the early structure of the disk and the inner stellar populations we see today. We know about this event not because we observed it happening, we weren't here, but because the chemical fingerprints and orbital patterns of stars in the halo still carry the signature of that ancient disruption. The galaxy remembers its past in the motion and chemistry of its stars. This is one of the most beautiful things about astronomy. The universe keeps records, not in books or databases, but in the orbits of stars, in the abundances of elements, in the direction and speed of ancient stellar streams. Every merger, every supernova, every collision is archived in the fabric of what came after. An astronomer studying the halo of the Milky Way is, in a very real sense, reading history. Not history written down, history written in light. Now, have you ever considered how the spiral arms of the Milky Way actually work? Because I think many people picture them as fixed structures, solid curving lanes of stars and gas rotating around the center the way the spokes of a wheel rotate. But that's not quite right. The spiral arms of the Milky Way are not made of fixed stars. They are patterns, density waves. Imagine a slow-moving traffic jam on a highway. The jam itself moves along the road, even though the cars that form it are constantly changing. As a car enters the jam, it slows down. As it exits, it speeds up again. The cars are moving. But the pattern, the jam, has a position and a motion of its own. The spiral arms of the Milky Way work exactly this way. The stars, gas, and dust are constantly moving through the arms. As they enter a region of higher density, they slow down, pile up, become compressed. The increased compression in gas clouds triggers the collapse and birth of new stars. These new stars, bright and young and burning hot, light up the arm with blue-white radiance. Eventually they drift out of the arm, and the arm moves on, finding new material to compress. The arm is not the stars. The arm is a wave moving through the stars, and we are orbiting inside one of these waves. Our sun slowly drifting through the Orion spur, a smaller structure between the larger Sagittarius and Perseus arms, which brings me to something worth considering carefully. Our location in the galaxy may not be random. We orbit at a distance from the center where the rotation speed of the spiral arms happens to roughly match the orbital speed of individual stars. This is called the corotation radius. Stars near this distance don't frequently cross through the spiral arms, which means they're not as often swept by the shock waves and radiation that accompany the dense, star-forming regions of the arms. Fewer close passages through stellar nurseries means fewer nearby supernova. Fewer supernova means fewer extinction-level radiation events. Our position in the galaxy, in this particular orbit, in this particular quiet spur, may have given life on Earth a stable enough environment over billions of years to evolve from simple chemistry into the complexity we see today. We may be alive, in part, because of where we live in the galaxy. Now let me slow things down a little, because we've been moving through enormous ideas, and I want to give you a moment to breathe and simply float. Close your eyes if they aren't already closed. Imagine you're looking at the Milky Way from above, far outside the galaxy, high above the galactic plane, looking down on the spiral. You can see the arms curving outward from the central bar. You can see the warm yellow glow of the core, thick with ancient stars, dense with mass and history. You can see the faint shimmer of the outer disk where star formation is still happening, but more slowly now. And beyond the visible disk, you can sense, even if you can't see, the enormous dark halo, extending far beyond the glow, holding the galaxy together with invisible gravity. This is your home seen from outside, a spiral in the dark, one of 200 billion galaxies in the observable universe. And yet, as far as we know, the only one that contains a civilization looking back at it. Let me return to the center, because there's more there that deserves your attention. When astronomers look toward the galactic core using infrared telescopes, which can penetrate the dust clouds that block visible light, they don't see a simple round ball of stars. They see a bar, a thick, elongated structure of stars crossing the central region of the galaxy, rotating slowly, acting like a stirring spoon in the inner disk. This bar is not an accident. It forms when stars in the inner regions drift inward and pile up along a central axis, reinforcing each other's gravity and creating a stable, elongated structure. The bar then influences everything around it. It channels gas inward toward the supermassive black hole at the center. It shapes the inner spiral arms, and it creates a distinctive peanut-shaped bulge visible in cross-section. The core of the Milky Way, viewed from the side, would look like a swollen, lumpy hourglass of stars. And within that bar, there may be something even stranger, hints of a second, smaller bar, tilted at a different angle, rotating independently. We can't see it directly. The dust is too thick, the distance too great. But its gravitational fingerprint shows up in the motion of surrounding stars and gas. The center of our galaxy is not one structure. It's a nest of structures, rotating and interacting and feeding material down into the black hole at the middle. It's astonishingly complex for something we can't even look at directly. Is star formation slowing down across the galaxy? Yes. Long ago, perhaps 10 or 11 billion years ago, the Milky Way was exploding with new stars. The gas was dense, the conditions were ripe, and stars were forming at rates far higher than today. But gradually, over billions of years, the available raw material has been consumed or heated or scattered. Many of the dense gas clouds have already collapsed into stars. The interstellar medium, while still present, is thinner and warmer in many regions than it once was. Today, the Milky Way forms new stars at perhaps a few solar masses per year, a slow, steady trickle compared to the stellar flood of the past. This doesn't mean the galaxy is dying. It means it's maturing. We are living in a quieter chapter of the Milky Way's life, a time of gradual consolidation rather than explosive creation. The galaxy is settling into a kind of middle age. And what about its future? Where is the Milky Way going? Not metaphorically, literally. Where is it physically traveling in space? The answer is strange and interesting. The Milky Way, along with the Andromeda Galaxy and about 50 other smaller galaxies, belongs to a gravitationally bound group called the local group. This collection of galaxies is drifting together through space, pulled by the gravity of larger structures beyond it. But within the local group, two galaxies dominate, the Milky Way and Andromeda, and they are approaching each other. Right now, Andromeda is over 2 million light-years away. To the naked eye on a clear, dark night in the northern hemisphere, it appears as a faint oval smudge near the constellation Cassiopeia. But it is moving toward us at roughly 110 kilometers per second. In about 4.5 billion years, roughly the current age of the solar system, the Milky Way and Andromeda will collide. Not immediately merge, but collide. The two spiral galaxies will begin to pass through each other, their stars so sparsely distributed that individual stellar collisions will be rare. But gravity will warp both galaxies into long tidal arms and streams. The shapes will be unrecognizable. After hundreds of millions of years of ongoing interaction, the two galaxies will merge into a single larger structure, sometimes called Milky Way, likely an elliptical galaxy, its spiral arms long since disrupted by the merger. What happens to the solar system in all of this? Almost certainly nothing dramatic. The Sun, the Earth, the other planets, all of them will continue orbiting, undisturbed by the stellar dance around them. The night sky will look very different. The stars will be rearranged. Perhaps the Andromeda galaxy's core will arc brilliantly across the sky during the merger. But the Earth, if it still exists by then, if it hasn't already been engulfed by an expanding sun, will still orbit. The merger of two galaxies is a slow, gravitational dance, not a demolition. Now let me ask you something before we go further. When you hear about stellar streams, those faint ribbons of stars scattered across the sky, the remnants of destroyed dwarf galaxies, does it feel like loss? Because in some ways, it is. A galaxy that existed for billions of years, containing its own population of stars, its own history, its own dark matter halo, has been gradually pulled apart by the tidal forces of the Milky Way and scattered into a thread of light thousands of light years long. Each star in that stream was once part of a different galactic neighborhood. It had stellar neighbors that are now gone, scattered across different quadrants of the Milky Way's halo. The dwarf galaxy's identity has been erased. Its stars now orbit the Milky Way as if they were always part of it. And yet, the Milky Way is built from these destructions. Every merger, every consumed dwarf galaxy, every tidal stream has added to the mass and richness of our own galaxy. Without these billions of years of accumulation, without the stars, the gas, the dark matter, the heavy elements donated by absorbed galaxies, the Milky Way would be a much smaller, much less complex place. We are the sum of many destructions. Perhaps that's true of most beautiful things. Do you ever think about what the galaxy looks like in light we can't see? Because the Milky Way we observe with our eyes is only one channel of a much richer broadcast. In radio wavelengths, the galaxy glows with the signals of hydrogen gas, pulsars and supernova remnants. In infrared, it reveals its hidden star-forming regions, the warm dust cloaking stellar nurseries that would otherwise be invisible. In X-rays, it blazes with the extreme temperatures of neutron star binaries and hot coronal gas. In gamma rays, it shimmers with the energy of cosmic ray interactions and the enormous Fermi bubbles above and below the core. Each wavelength reveals a different structure, a different population of objects, a different chapter in the galaxy's story. We tend to think of the Milky Way as what we see on a dark night, that pale river of overlapping stars. But the full picture is infinitely richer. The galaxy is broadcasting in dozens of frequencies simultaneously, and we've only learned to receive a few of them. Let me tell you about pulsars, because they are among the strangest and most precise objects we've ever discovered. When a massive star dies in a supernova, the core left behind, a neutron star, may be spinning rapidly, very rapidly. Some neutron stars rotate hundreds of times per second, and as they spin, they emit beams of radio waves from their magnetic poles. If one of those beams sweeps past the Earth, we detect a regular pulse, a precise repeating radio signal, blinking as reliably as the most accurate clock ever made. These are pulsars, and their regularity is extraordinary. Some are so precisely timed that they rival atomic clocks in stability. Astronomers use pulsars to measure distances across the galaxy, to test theories of gravity, and to search for gravitational waves. They are the galaxy's metronomes, left behind by death, blinking steadily in the dark. And since we're talking about things that pass through the galaxy invisibly, let me tell you about neutrinos. Every second, trillions of neutrinos, ghostly, nearly massless particles produced in nuclear reactions pass through your body. Most of them come from the sun, but some come from much farther away. Supernova explosions produce enormous bursts of neutrinos, so intense that in the brief seconds of the stellar collapse, more neutrinos are produced than the sun will emit across its entire billion-year lifetime. Some of these ancient neutrinos, produced in supernova explosions from the far reaches of the galaxy, are passing through you as you lie there, through your body, through the Earth, through everything. They interact with ordinary matter so rarely that billions of them cross the planet every second, and the planet barely notices. Special detectors buried deep underground or frozen in Antarctic ice wait patiently to catch just a few. The rare flash of light from a neutrino's chance collision with an atom. Neutrinos carry information from the galaxy's most violent events, and most of the time, they carry it right through us without stopping to say hello. Let's talk about globular clusters. These are some of the oldest and most beautiful structures in the Milky Way. Compact spheres of stars, sometimes containing hundreds of thousands of suns packed into a volume just a few dozen light-years across. The Milky Way has more than 150 of them, orbiting the galactic center out in the halo, like ancient satellites around an ancient world. The stars inside globular clusters are among the oldest in the galaxy, many more than 12 billion years old, some possibly older than the Milky Way's disk itself. Their chemistry tells the story of the early universe, when heavy elements were still scarce, when only the lightest atoms had yet been forged and scattered. In a globular cluster, if you stood on a planet orbiting one of its stars, the night sky would be stunning beyond anything imaginable from Earth. Stars packed so close together that the night would never truly be dark. Multiple stars near enough to shine as bright as a full moon. A sky blazing with ancient light, but there's a catch. Globular clusters, being so old and so dense, may not be the most hospitable places for life. The high stellar density means frequent gravitational encounters between stars, which can destabilize planetary orbits. Radiation from nearby stars can strip atmospheres. The dense central regions may see stellar collisions, two stars merging into one, creating what are called blue straggler stars, objects that appear younger than their neighbors, because the merger has essentially recharged their fusion fuel. Globular clusters are magnificent time capsules from the early universe, but they might be difficult places to evolve in peace. Now, gently, let's talk about what lives between the stars. The space between the stars is not empty. This is one of the most important corrections in our understanding of the galaxy. The interstellar medium, the thin mixture of gas, dust, and plasma that fills the space between stars, is complex, structured, and astonishingly active. It includes cold, dense molecular clouds where stars are born. It includes warm, diffuse hydrogen gas glowing faintly in red light. It includes hot, ionized plasma heated by nearby supernova and stellar winds. It includes magnetic fields threading through the disk, guiding the motion of charged particles and influencing how clouds collapse and how cosmic rays travel. It includes shock waves from supernova traveling outward at thousands of kilometers per second, compressing the medium, triggering new star formation, heating gas to millions of degrees. The interstellar medium is not a void. It's a turbulent, multi-phase ecosystem, constantly stirred and reshaped by the stars embedded within it. And within that interstellar medium, within its coldest and densest clouds, something remarkable has been found: organic molecules, complex carbon-based compounds, polycyclic aromatic hydrocarbons, simple sugars, amino acid precursors. the basic building blocks of chemistry that, on Earth, led to life. These molecules form in the atmospheres of dying stars and within the cold interiors of molecular clouds, shaped by cosmic rays and ultraviolet radiation. They drift through the galaxy on microscopic dust grains, traveling billions of kilometers, settling into the gas clouds that collapse into new stars and new planetary systems. Some of these molecules may have arrived on the early Earth, carried by comets and asteroids, contributing to the chemical inventory from which life emerged. The galaxy is not just making stars, it is making chemistry, and perhaps, through that chemistry, making life. Can I tell you something about the Milky Way's magnetic field? It's easy to forget, because we rarely think about magnetism at galactic scales. But the Milky Way is laced with a magnetic field that extends across the entire disk, rising into the halo, weaving through the interstellar medium in vast patterns we're still learning to map. The field is weak by earthly standards, millions of times weaker than a refrigerator magnet. But across galactic distances, it has real and measurable effects. It shapes how cosmic rays travel through the galaxy, bending their paths and confining them. It influences how dust grains align in space, causing them to polarize the starlight that passes through them. It can affect the collapse of gas clouds, adding pressure that resists gravity, potentially slowing or directing star formation. And it forms loops and arcs above and below the galactic plane, towering magnetic structures that we're only beginning to understand. The galaxy is not just a gravitational structure. It is an electromagnetic one. It hums with a magnetism that is ancient, distributed, and quietly powerful. Now, before we slow towards sleep completely, let me ask you one final lingering question. Do you think the Milky Way is typical? Of the hundreds of billions of galaxies we can observe in the universe, is ours unusual in any way? The honest answer is, we're not sure. The Milky Way is a barred spiral galaxy, which is a common type. It's not particularly large by galactic standards, but not small either. Its central black hole is massive, but not the most massive known. It sits in a relatively modest galaxy group, the Local Group, which is itself a member of the much larger Virgo supercluster. In some ways we might be average, but in others we might be unusual. Our position in the galactic habitable zone is not guaranteed for every spiral galaxy. Our relatively quiet central black hole, compared to galaxies with active quasar nuclei, may have allowed complex structures to form without constant radiation disruption. The Magellanic Clouds, our largest satellite galaxies, may be newcomers rather than long-standing companions, which means we're currently experiencing a gravitational perturbation that other spiral galaxies with stable satellites don't share. Whether the Milky Way is typical or unusual in ways that matter for the emergence of life is a question we genuinely cannot yet answer. But the question is worth holding, quietly. As you drift, let me spend a little time with something I find endlessly calming. Stellar streams. We've mentioned them before, but let's sit with the image. Across the halo of the Milky Way, stretched out in long, thin arcs, some of them tens of thousands of light-years long, are ribbons of stars that were once part of other galaxies or the outskirts of globular clusters. Tidal forces from the Milky Way's mass have stretched and shredded these structures, smearing their stars across the sky in delicate, curved threads. Most are invisible to the naked eye. Many were invisible to any telescope, until surveys like Sloan and Gaia mapped the positions and velocities of millions of stars in detail. Now we see them, ghostly rivers of ancient stars, tracing the paths of their former homes, orbiting the Milky Way in slow, majestic loops that take hundreds of millions of years to complete. Some of these streams are so faint, so dispersed, that distinguishing their member stars from the background of the halo requires careful statistical analysis. But they're there. The Sagittarius stream, the Orphan stream, the Styx stream, the GD1 stream, each one a different destroyed structure, each one a record of a gravitational encounter. The halo of the Milky Way is a museum of destructions, a gallery of past encounters. The sky is full of the remnants of things that no longer exist in the form they once had. Now, while you rest, I want to take you through something that the Milky Way does over vast timescales that I find almost meditative to think about: the galactic fountain. Above and below the flat disk of the Milky Way, gas is constantly flowing. Supernova explosions and the intense stellar winds of massive stars heat the interstellar medium, creating enormous bubbles of hot gas that expand and push upward, punching through the disk and venting into the halo. This gas rises, slowly by cosmic standards, but rising nonetheless, carrying with it heavy elements forged in the stellar explosions that drove it out. As it rises into the cooler halo, it begins to slow and cool. Eventually, it condenses, and it falls back down, a slow cosmic rain of enriched gas returning to the disk, where it will eventually join a molecular cloud and collapse into new stars. The galaxy breathes. It exhales superheated gas through chimneys above the disk and inhales it back as cool, enriched clouds returning to the plane. The cycle repeats over hundreds of millions of years. The Milky Way is not a static structure. It circulates, and similarly the galaxy is not a closed system. It doesn't just recycle its own material. It draws in fresh gas from outside itself. The cosmic web, the enormous, large-scale structure of the universe, made of filaments of dark matter and gas connecting galaxy clusters like threads in a cosmic spider's web, delivers material to galaxies continuously. Long, tenuous streams of gas fall inward from the intergalactic medium, slipping into the halo, eventually reaching the disk, eventually joining the cycle of star formation. The Milky Way drinks from the cosmic web. It is always receiving new material, always incorporating outside mass into its own ongoing story. Let me tell you about the corrotation radius one more time, but more gently this time, because I think it's one of the most quietly important facts about our place in the galaxy. The spiral arms of the Milky Way rotate at a certain speed. Individual stars orbit at their own speeds, depending on their distance from the center. At most distances, these speeds are different. Stars move faster or slower than the pattern of the arms, but at one specific distance from the center, the speeds match. A star at this distance orbits the galaxy at almost exactly the same speed as the spiral arm pattern. This means the star doesn't frequently pass through the arm. It doesn't repeatedly encounter the dense, radiation-intense, supernova-heavy environments inside the arms. It drifts in relative peace, in the quiet space between the arms' passages. Our Sun orbits near this corrotation radius. We have been, for billions of years, riding roughly in step with the galaxy's spiral arms, not swept repeatedly through their dangerous hearts, but hovering at the edge of the pattern, in a relatively calm corridor. Some astronomers think this may be one of the reasons complex life had the time to evolve on Earth. The galaxy, in its structure and its dynamics, may have provided us a protected lane. Not because it meant to, simply because the mathematics of its rotation happened to place a quiet zone at exactly the distance where our Sun orbits. The universe didn't choose us, but we may have found ourselves, by sheer orbital coincidence, in exactly the right place, As we move toward the close of our journey, I want to give you something for the very edge of sleep, something to carry you across. The oldest light that reaches your eyes on a clear night left its source years ago, in some cases thousands of years ago. You are not seeing the star as it is. You are seeing the star as it was, sometimes before your earliest ancestors built the first cities. The galaxy you see is not the galaxy that currently exists. It is a mosaic of different moments, different pasts, layered together in one simultaneous sky. The light from nearby stars left them years or decades ago. The light from the galactic center, if it could reach your eyes without dust in the way, would have left its source 26,000 years ago, when our ancestors were drawing animals on cave walls in France. The galaxy is not just a place. It is a time machine. Every direction you look, you're looking backward. Every point of light is a message from the past, crossing the void to reach your retina in this exact moment, on this exact night, as you lie there and breathe slowly in the dark. And the Milky Way, for all its scale, for all its 100 billion stars and its dark matter and its ancient mergers and its orbiting black hole, is still only one galaxy among 200 billion in the observable universe. And the observable universe is only the portion we can see, the sphere of space from which light has had time to reach us since the Big Bang. Beyond that horizon, the universe continues. Stars burning in galaxies we will never see, mergers happening in silence across distances that light will never bridge for us. A cosmos so vast that our most powerful telescopes are like pinpricks in a wall, letting through just enough light to tell us that the darkness on the other side is not empty. And within all of that vastness, all of that ancient, ongoing, violent, creative, patient, indifferent cosmos, here you are, a warm creature on a wet rock orbiting a middle-aged star in the outer arm of a spiral galaxy, in a small cluster of galaxies, in a larger supercluster, in a universe 13.5 billion years old. You are cosmically tiny, and you are cosmically precious. Because as far as we know, you are one of the places the universe has learned to look at itself, to wonder, to ask where it came from, where it's going, and whether there is anyone else out there asking the same question. The Milky Way doesn't care whether you sleep or stay awake. It doesn't know you exist. It will keep turning for billions of years after you, and everything you've ever known is gone. And somehow, that is the most comforting thought I know, because it means the universe was beautiful before you, and it will be beautiful after you. And right now, in this quiet moment, you are the part of it that is aware of that beauty. Let your breath slow. Let the thoughts untangle. The galaxy is turning. Stars are forming in cold clouds hundreds of light years away. A rogue star is crossing the void between galaxies. A pulsar is blinking steadily in the dark. Neutrinos are passing through you right now, gentle and invisible and ancient. The Magellanic Clouds are completing their slow first orbit of our home. Somewhere in the halo, a star older than the galaxy's disk is burning softly, having waited 13 billion years to be noticed. You don't have to understand it all. You don't have to hold it in your mind. You can simply be in it. Floating in the spiral arm of a quiet galaxy, on an ordinary night as the universe goes about its business, sleep well. Dream softly. The Milky Way will still be there when you wake up. It always is. Good night. But wait, don't drift away just yet. There are still so many quiet corners of the Milky Way we haven't visited. And the strangest ones, perhaps, are saved for last. So let your body stay heavy where it is. Let your breathing stay slow. And let me carry you just a little further into the dark. Have you ever thought about what it means that we don't know how many arms the Milky Way has? It's such a fundamental question, like not knowing how many floors are in the building you live in. And yet, despite decades of observation, astronomers still debate the exact number and extent of the Milky Way's spiral arms. The problem is our location. We sit inside the disk, peering outward through layers of gas and dust, trying to map structures that span tens of thousands of light-years when our instruments can only see a few thousand light-years clearly in some directions before the dust becomes impenetrable. It's like trying to map the coastline of a continent while standing in the middle of a forest on that coast. For a long time, textbooks said 4 major arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm, and a smaller spur, the Orion spur, where our sun resides. But more recent surveys, using radio telescopes that can pierce through the dust, and the extraordinary data from the Gaia spacecraft, suggest the picture is more complex. Some arms appear to fragment or bifurcate. Some seem to fade and strengthen at different points along their length. The galaxy may not be a clean, symmetric, 4-armed spiral at all, but something more ragged and irregular. A pattern imposed on underlying randomness, beautiful from a distance but full of irregularities up close. Like most beautiful things. And do you know what the Gaia spacecraft has done for our understanding of the Milky Way? It has been quietly revolutionary. Launched by the European Space Agency in 2013, Gaia has spent years measuring the positions, distances, and motions of more than 1 billion stars with extraordinary precision. Precision that allows astronomers to reconstruct 3-dimensional maps of the galaxy and trace the motions of stars backward and forward through time. From Gaia's data, scientists have discovered stellar streams that were previously invisible. They've mapped the warp of the galactic disk in greater detail than ever before. They've identified the signatures of ancient mergers in the orbital patterns of halo stars. They've confirmed that the sun bobs gently above and below the galactic plane as it orbits. And they've given us, for the first time, a dynamic picture of the galaxy. Not a snapshot, but a movie, showing how stars have moved and will move. Gaia is the closest thing we have to truly seeing the Milky Way from outside. Not from above, not from a distance. We're still trapped inside, but with enough precision that we can reconstruct what that external view would look like. It is a remarkable technological achievement, sitting in the quiet routine of data transmission. A small spacecraft 1 million miles from Earth, counting stars one by one. Now let me ask you something that might seem strange at first. What do you think it would be like to live on a planet in a globular cluster? One of those ancient, dense spheres of hundreds of thousands of stars orbiting the Milky Way's halo. We touched on this briefly, but let's go deeper. In the densest globular clusters, stars are packed together so tightly that they're separated by distances of light weeks, not light years. Our nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years away. In the core of a globular cluster, that distance might be reduced to a fraction of a light-year. On the surface of a planet in such a cluster, if stable planets can exist there at all, given the constant gravitational nudges from nearby stars, the night sky would be unimaginable. Not dark, never fully dark. Thousands of stars close enough to cast shadows. A sky so crowded with light that night would simply be a dimming, not a darkening. A sky where multiple stars burned bright enough to be visible at noon, visible alongside the sun itself. For early astronomers on such a world, the challenge would not be seeing stars. It would be making sense of the overwhelming number of them. Navigation by stars would be an incomprehensible task. and the recognition that space was mostly empty, that stars were enormously distant from each other, would come much later. Because from inside a globular cluster, they are not. The universe would feel smaller, more intimate, more crowded, and yet perhaps no more familiar, no more knowable. We are lucky, in a way, to live somewhere quieter, where the night sky is dark enough to see, but not so crowded that it overwhelms, where the stars are few enough to name, to group into constellations, to use as a map. Our sky, sparse as it sometimes feels, is perfectly scaled for wonder without chaos. Let me tell you something about the interstellar medium that I find almost meditative to sit with. The gas between the stars exists in several distinct phases, and they coexist across the galaxy in a kind of thermal equilibrium maintained by the energy input of stars and supernova. There is the cold neutral medium, dense clouds of hydrogen, just a few tens of degrees above absolute zero, dark and dormant, waiting for a gravitational nudge to collapse. There is the warm neutral medium, more diffuse hydrogen at temperatures of a few thousand degrees, filling much of the galactic disk. There is the warm ionized medium, hydrogen heated and ionized by ultraviolet light from hot young stars, glowing in faint emission lines detectable by radio telescopes. And there is the hot ionized medium, gas heated to millions of degrees by supernova shockwaves forming vast, tenuous bubbles and the hot plasma that fills much of the volume between the galaxy's denser structures. These four phases are in rough balance, constantly exchanging mass and energy. Supernova heat the hot phase. The hot phase slowly cools and condenses. Condensed gas forms cold clouds. Cold clouds collapse into stars. Stars heat their surroundings and eventually explode into supernova. The cycle continues, as it has for billions of years, as it will continue for billions more. The interstellar medium is not background, it is the engine. And within that engine, something extraordinary happens with magnetic fields. The galaxy's magnetic field doesn't just thread passively through the interstellar medium, it actively shapes it. When a molecular cloud begins to collapse towards star formation, the magnetic field threading through it provides a pressure that opposes the collapse. Gas can flow along field lines relatively freely, but moving across field lines requires more energy. This means that the magnetic field can slow or channel the collapse of a cloud, influencing how many stars form, how quickly, and in what configuration. In the densest clouds, the magnetic field is eventually overcome. Gravity wins, the collapse proceeds, but in more diffuse regions, the magnetic field can hold clouds in suspension, preventing collapse for millions of years longer than gravity alone would allow. The Milky Way's magnetic field is not just a curiosity. It is a governor of star formation, an invisible hand shaping the rate at which the galaxy produces new suns. Now, and here is a question worth asking very slowly. In the quiet just before sleep, do you think there are other civilizations in the Milky Way? Not in other galaxies, just in ours, just among the 100 billion to 400 billion stars of the galaxy you call home. We have been searching, formally, for extraterrestrial intelligence since the early 1960s. Radio telescopes have swept the sky for artificial signals, narrowband transmissions, laser pulsars, techno-signatures. So far, silence, but the silence is not necessarily an answer. We have searched a tiny fraction of the galaxy with a tiny fraction of the techniques available to us. The Milky Way is vast. Radio signals travel at the speed of light and the galaxy is 100,000 light years across. A civilization on the far side of the galaxy that began transmitting when the pyramids were being built is still more than 95,000 light years away from us. Their signals haven't reached us yet. The question of life in the galaxy touches everything we've discussed tonight. The right elements, forged in dying stars. The right chemistry, assembling in cold clouds. Stable planetary orbits in galactic habitable zones. Enough time, billions of years, for complexity to emerge. All of these conditions are met repeatedly throughout the galaxy. Whether the final step, the emergence of something that looks at the sky and wonders, happens commonly or rarely, we genuinely don't know. But the galaxy gives it every reasonable chance. Let me slow further. Let me walk you through something at a quieter pace. The sun will die one day. Not for another 5 billion years or so, which is an incomprehensible span of time, roughly equal to the sun's current age again. But eventually, the sun will exhaust the hydrogen in its core. Fusion will shift to its outer layers. The sun will expand, slowly at first, then more rapidly, swelling into a red giant, engulfing Mercury, Venus, and possibly Earth in the process. The outer layers will puff outward in a glowing shell called a planetary nebula, a beautiful ring-shaped cloud of ionized gas lit from within by the hot core left behind. And that core, a dense, cooling object about the size of the Earth, but with half the sun's original mass, will become a white dwarf. White dwarfs are the most common final state for stars like the sun. They don't undergo fusion. They simply radiate stored heat, gradually cooling over trillions of years. In 100 trillion years, far longer than the current age of the universe, the sun's white dwarf will have cooled to match the temperature of space itself, becoming a cold, dark cinder orbiting in the dark. A black dwarf, but the material of the sun, the hydrogen, the helium, the carbon, the oxygen built up over its lifetime, will not be lost. Some of it will be scattered by the planetary nebula into the interstellar medium. It will cool, condense, and eventually join a molecular cloud. And from that cloud, perhaps billions of years from now, new stars will form, new planets, new worlds. The sun is not eternal, but its matter is. It will continue in different forms as long as the galaxy persists. Now I want to tell you about something called blue straggler stars, because they are among the universe's more peculiar characters. In a globular cluster, where all the stars formed at roughly the same time from the same cloud, you'd expect a uniform distribution of ages. Old stars should look old, reddish, dimmer, beginning to expand. But scattered among the cluster's population, astronomers find a handful of stars that appear younger, bluer, hotter, more luminous. Stars that look like they shouldn't be there, based on the cluster's age. These are blue stragglers, and the most widely accepted explanation is that they are the products of stellar mergers. Two stars in a tight binary system have spiraled together, perhaps nudged by a close gravitational encounter with another star, and merged. The merger has combined their hydrogen reserves, essentially giving the resulting star a fresh supply of fuel and making it appear younger than its surroundings. There's something deeply interesting about this. In the crowded environment of a globular cluster, stars occasionally touch, occasionally merge. Two separate stellar lives become one, and the result appears reborn. A blue, hot, luminous star burning in a cluster of ancients, conspicuous precisely because it defies the expected pattern of aging. The universe, it seems, occasionally arranges for second acts. Are you still here? Good. Then let me offer you something truly enormous. The question of the Milky Way's mass. You would think that measuring the mass of our own galaxy would be something we could do with confidence. But it remains genuinely uncertain, and the uncertainty is large. Current estimates suggest the Milky Way's total mass, including its dark matter halo, is somewhere between 700 billion and 2 trillion times the mass of the Sun. That factor of roughly 3 between the lower and upper estimates is enormous. We're uncertain about the mass of our own home by a factor of 3. The reason is dark matter. We can measure the mass of the visible components, the stars, the gas, the dust, with reasonable accuracy. But dark matter is invisible, and its distribution beyond the visible disk of the galaxy is difficult to constrain. We infer its presence from the orbits of distant stars and globular clusters, but our sampling of those distant orbits is incomplete. Better constraints are coming, from Gaia's ongoing measurements, from pulsar timing arrays, from future telescopes. But for now, the Milky Way's true weight remains one of its more quietly humbling secrets, and interestingly, this uncertainty matters for the future. When the Milky Way and Andromeda eventually collide and merge, the relative masses of the two galaxies will determine the dynamics of the merger, which one's black hole ends up at the center of the merged system, how the stars are redistributed, what shape the final galaxy takes. For decades, astronomers assumed Andromeda was more massive based on its slightly larger apparent size. But some recent measurements suggest the Milky Way's dark matter halo may be more massive than previously thought, possibly even more massive than Andromeda's. If so, our galaxy may be the more dominant partner in the merger that lies 4.5 billion years in the future. The quiet one, it turns out, may be carrying the greater weight. Let me take you to one more place before we truly let go for the night. Somewhere in the halo of the Milky Way, high above or below the flat disk, drifting in a long, tilted orbit that takes hundreds of millions of years to complete, there is a star. It is faint, small. Its surface is cooler than the Sun's, burning with a dim orange-red glow. Most people who've ever looked at the night sky have never noticed it. But this star is extraordinary for one reason. It is very possibly the oldest star in the galaxy. It was given the name SMSS J0313.36670839.3. Not a romantic name, but astronomy often isn't. Its atmosphere contains almost no iron, no calcium, almost nothing beyond hydrogen and helium. Its chemical composition is the signature of a star born before generations of supernova had enriched the universe with heavy elements. Astronomers estimate it formed more than 6 billion years ago, within 200 million years of the Big Bang itself. It is as close to a firstborn star as we've ever found, a star that was already ancient when our galaxy was taking shape. A star that has been burning, quietly, faithfully, without much fanfare, for almost as long as time itself. And it is still there, drifting in the halo, completing its slow orbit, shining its dim orange light into the dark. It has watched galaxies form around it. It has watched the Milky Way assemble from a million smaller structures. It has watched stars form and die across hundreds of generations while it continues, unchanged, at the very edge of the galaxy's ancient memory. If you could stand on a world orbiting that star, and we don't know if any world exists there, and look out at the galaxy below you, you would see a different Milky Way than the one we see today. More chaotic, still assembling, still violent with mergers and explosions and the early, furious business of galaxy formation. But the star itself, where you stand, would be quiet, just as it has always been, burning its hydrogen slowly, patiently, with the steadiness of something that has outlasted everything it was born alongside. That star, I think, is a good thing to imagine as you fall asleep, not because it's comforting in any obvious way, but because it puts things in perspective. In 13.6 billion years of cosmic history, wars, extinctions, collisions of galaxies, the deaths of trillions of stars, That small, dim, ancient sun has simply continued, turning hydrogen to helium, one quiet nuclear reaction at a time. You don't have to hold the whole galaxy. You don't have to understand its full history, or map its spiral arms, or know the mass of its dark matter halo. You just have to continue. One breath at a time. One heartbeat at a time. In the halo of something ancient and enormous and beautiful, the Milky Way will keep turning tonight while you sleep. Sagittarius A star will pulse faintly at the center. Somewhere, a molecular cloud will begin its slow million-year collapse towards starhood. A stellar stream will continue its quiet, invisible arc across the halo. A neutron star will tick its faithful pulsar rhythm into the void. The Magellanic Clouds will move a tiny increment closer on their first orbit around our home. And you, in your warm room, in your breathing body on your quiet planet, orbiting your ordinary star in the outer arm of a barred spiral galaxy in a small corner of an unimaginably large universe, you will sleep. That is enough. More than enough. It is, in fact, everything good night. But actually, one more thing. Just one more. I promise it's worth staying awake for. Have you thought yet about what it means that gravity travels at the speed of light? Not just light, gravity itself. When Sagittarius A star, the supermassive black hole at the center of the Milky Way, tugs on the sun, that gravitational influence doesn't arrive instantly. It left the galactic center 26,000 years ago. It has been traveling across the galaxy at the speed of light, crossing gas clouds and stellar nurseries, and the quiet space between stars, and it is arriving at the sun right now. The gravity you feel from the galactic center, the force that keeps the solar system in its orbit, is 26,000 years old. You are responding, right now, to a gravitational message sent when our ancestors were beginning to develop agriculture, when the first cities were still thousands of years in the future, when the most complex human technology was a flint tool and a fire. This is true for every force in the universe. Nothing propagates faster than light. No information, no influence, no force. Which means that the universe we observe and the universe we interact with is always the past. We are never in contact with the present state of anything beyond our immediate surroundings. The sun's light takes 8 minutes to reach us, so the sun we see is 8 minutes old. The nearest star, Proxima Centauri, is 4.2 light-years away, so the Proxima we see left 4.2 years ago, and we don't know what it looks like today. The galactic center is 26,000 light-years away. Andromeda is 2.5 million light-years away. The most distant visible galaxy, GNZ 11, is so far away that the light we detect left it 13.4 billion years ago, when the universe was only 400 million years old. The galaxy we observe may not even exist anymore in the same form. We live surrounded by the past. The universe presents itself to us as a fossil record. Layers of time compressed into a single, simultaneous sky. Every night you look up, you're looking into an archive, not a photograph. A library, with volumes spanning billions of years, all open at once, and the Milky Way, your galaxy, your gravitational home, is part of that archive. Its oldest stars carry the chemistry of the universe's first billion years. Its youngest stars are still forming, in clouds that have been contracting for only a few million years, the blink of an eye on a galactic timescale. Its spiral arms carry the compressed echo of density waves that have been moving through the disk for billions of revolutions. Its dark matter halo contains material that has been gravitationally bound to this structure since before the Earth existed. The Milky Way is not just a place in space. It is a document in time. Now, and here is one of the most beautiful, subtle facts we'll visit tonight. The sun itself is not where it was born. No star is. Over billions of years, gravitational interactions with other stars, with giant molecular clouds, with the pattern of the spiral arms, gradually shift a star's orbit. Not dramatically, not in a single generation. But over billions of orbits around the galactic center, a star can migrate inward or outward by significant distances. Our Sun, based on its current chemical composition, which is slightly richer in heavy elements than you'd expect for a star at its distance from the galactic center, may have formed a bit closer to the center, in a region where star formation was more active and heavy element enrichment was higher. Over its 4.6 billion years of life, it has slowly drifted outward to its current position. The solar system's address has changed. Not the house number, but the zip code, at least, and the Sun's siblings, the stars it formed alongside in its birth cluster, are scattered across the galaxy. Over billions of years, the birth cluster has dissolved. Stars peeled away by tidal forces and gravitational encounters, drifting to different orbits, different positions in the disk or halo. We don't know where the Sun's siblings are. They're out there. Stars born from the same cloud of gas, carrying similar chemical fingerprints, now separated by thousands of light years. Astronomers using Gaia data are actively searching for them, comparing chemical abundances, orbital properties, ages. A few candidate solar siblings have been identified, stars that might have grown up alongside our Sun in the same stellar nursery before time and gravity carried them away. It's one of the lonelier thoughts in astronomy when you sit with it. A family scattered across 100,000 light years, each star burning quietly in its own corner of the galaxy, unaware of its siblings, carrying the same chemical memory of a birth long forgotten. Let me spend a moment with something that operates at the very opposite extreme of scale. Not the whole galaxy, but a single phenomenon within it. Variable stars. These are stars that change in brightness over regular intervals, pulsing in and out over hours, days, or weeks as their outer layers expand and contract. The most useful for astronomy are called Cepheid variables, named after the first well-studied example in the constellation Cepheus. Cepheids pulse in a remarkably consistent way. The longer the period of the pulse, the more luminous the star. This period luminosity relationship means that once you measure how long a Cepheid takes to pulse, you know its true brightness. And by comparing its true brightness to how bright it appears in the sky, you can calculate its distance. It's a form of cosmic distance measurement so reliable that it's called the standard candle. In the early 20th century, an astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory, cataloging stars rather than conducting research as she would have liked, noticed this relationship in Cepheid variables in the Magellanic Clouds. Her discovery of the period luminosity relationship became one of the most important in the history of astronomy. It allowed Edwin Hubble, a decade later, to measure the distance to Andromeda and demonstrate definitively that it lay far outside our own galaxy, that the universe contained billions of galaxies beyond the Milky Way, each containing billions of stars. The modern cosmological picture of the universe begins, in a very real sense, with Leavitt's careful cataloguing of pulsing stars in the Magellanic Clouds. Variable stars still blink quietly across the galaxy today, measuring themselves for anyone patient enough to watch. Now here is something that might help you understand the Milky Way's size at the most human level possible. Light travels at approximately 300 zero-zoned kilometers per second, fast enough to circle the Earth more than 7 times in a single second. and the Milky Way is approximately 100,000 light-years in diameter. That means that to cross the galaxy, from one edge of the disk to the other, traveling at the speed of light, would take 100,000 years. 100,000 years. Not 100,000 hours. Not 100 Zuzone days. Years. At the speed of light, our fastest spacecraft, the Voyager probes, launched in 1977, now nearly 24 billion kilometers from the Sun, are traveling at roughly 17 kilometers per second. At that speed, to cross the Milky Way would take approximately 1.7 billion years, almost half the current age of the galaxy. We have built nothing that could traverse it in a human lifetime. We have built nothing that could traverse it in the lifetime of our civilization. The galaxy is not just large in the abstract. It is unreachably large by any measure we have ever applied to speed and distance, and yet every point of light you see in the sky is within it. Every star visible to the naked eye, every constellation, every smear of the Milky Way across the summer sky, all of it is within 100,000 light-years of us. All of it is local in galactic terms. The nearest large galaxy beyond our own is Andromeda, at 2 to 5 million light-years, 25 times the diameter of the Milky Way, and there are galaxies far beyond that, billions of light-years in every direction. The scale increases at every level. The universe is not just larger than we imagine. It is larger than we are capable of imagining, even when we try. And there's something else about scale worth sitting with as you drift. The supermassive black hole at the center of the Milky Way, Sagittarius A star, 4 million solar masses, event horizon spanning tens of millions of kilometers, is, relative to the galaxy, impossibly small. The galaxy is 100,000 light-years across. The black hole's event horizon is roughly 24 million kilometers in diameter, which sounds enormous, but is in fact far smaller than the distance from the Earth to the Sun. On a galactic scale, the black hole is a microscopic point, a marble in the center of a city, and yet its gravity organizes everything. Its mass shapes the orbits of stars for thousands of light-years in every direction. Its past activity echoes across tens of thousands of light-years in the Fermi bubbles. Its appetite for gas and stars determines how much material flows through the galactic center and out into the disk. The smallest significant object in the galaxy, by size, is also its most powerful, by gravity. Scale and power are not always proportional. Sometimes a small, dense thing is the axis around which everything else turns before I let you go completely. And I will let you go. Very soon. I want to give you one more image, one more place to take with you into the dark behind your eyes. Imagine a night, far in the future, 4.5 billion years from now. A night on a world orbiting some surviving star, somewhere in what was once the outer disk of the Milky Way. The sky above this world looks nothing like the sky above the Earth tonight. The two great spirals, the Milky Way and Andromeda, have been merging for hundreds of millions of years. Their spiral arms have been pulled into vast tidal streams. Their central bars have been disrupted. The gas clouds that once wound through the arms have been compressed and agitated, triggering enormous bursts of star formation that lit the merging galaxies from within. Seen from a distance, during the peak of the merger, the combined system would have looked like two fireworks displays happening simultaneously, arcing light across millions of light-years. But now, a long time later, it has quieted. The two galactic cores have merged. The supermassive black holes at the center of each galaxy have found each other, spiraled together, and merged into one, a single, enormous black hole at the center of the new combined structure. The spirals are gone. What remains is a large elliptical galaxy, a smooth, featureless oval of ancient stars, their orbits now randomly distributed in all directions rather than the orderly disk rotation of the old spirals. Star formation has nearly stopped. The gas has been used up or expelled. What remains is a vast, quiet congregation of old stars, slowly cooling in the dark. Somewhere in that elliptical galaxy, drifting in whatever orbit the merger left it in, is the descendant of the solar system, or at least the white dwarf remnant of the Sun, cool and dark, with no planet left to orbit it. The Earth will have been long since consumed by the expanding Sun, billions of years before the merger even began. But the Sun's matter persists. It is part of the new merged galaxy, incorporated into its history, its chemical makeup, its halo. Nothing is lost. Matter is rearranged, recycled, redistributed. The Milky Way will not die. It will become something else, as it always has, as it always will. You are part of a story that has no ending, only transformation. The atoms of your body will outlast everything you've ever known. They will be part of stars not yet born, planets not yet formed, perhaps life not yet imagined. The universe doesn't have a recycling bin. It has a recycling engine, and it never stops running. So when you look at the night sky, when you look at that quiet band of light crossing the dark above you, know that you are looking at home. Not just the planet beneath you, not just the solar system around you, but the whole enormous, ancient, slowly turning, dark matter-laced, spiral-armed, black hole-centered, globular cluster orbiting, neutron star blinking, supernova stirring, stellar stream trailing, magnetically threaded, gravitationally warped, chemically rich, cosmically ordinary, and yet absolutely extraordinary Milky Way, your galaxy, yours. Now let it carry you. Let the turning of the disk be the thing that rocks you gently into sleep. Let the slow, patient orbit of the solar system be the cradle. Let the fact that everything is in motion, but nothing feels like it. From here be the reason you can rest. You don't have to move. The galaxy is moving for you. It always is. Sleep now. The stars will still be there in the morning, a little further along in their orbits. The galaxy a little further along in its year. And you will wake into the same ancient, beautiful, incomprehensible home. Good night. Truly, good night. Still here? Then you must be the kind of person who finds the darkness too rich to leave just yet. And that's fine. That's more than fine. Because there is one more layer to the Milky Way that we haven't fully visited. The layer that exists not in infrared or radio or gamma rays, but in pure mathematics. The layer of the galaxy that we know not through any telescope, but through equations. The Milky Way obeys the laws of physics. This sounds obvious, but it's actually one of the most profound things we can say about it. Gravity, electromagnetism, the strong and weak nuclear forces, the same fundamental rules that govern a falling apple or an electron in a laboratory govern the orbit of a star around a black hole 4 million times the mass of the Sun. The universe does not make exceptions. The same equations that Isaac Newton wrote down in the 17th century, that Einstein refined in the 20th, that quantum mechanics extended to the subatomic level. These equations describe the Milky Way with the same reliability they describe an experiment on a tabletop. The galaxy is enormous and ancient and mostly invisible, but it is knowable. It follows rules. And because it follows rules, we can understand it, even from inside it, even without ever seeing it from outside. This is, when you think about it, one of the most remarkable facts of all. The universe is comprehensible. Not fully, not yet. But the fact that human minds evolved to navigate a savanna, to hunt to find water, to raise children, can formulate equations that accurately describe the behavior of objects billions of light years away, objects that existed before the Earth was born. This is astonishing. There is no reason, from an evolutionary standpoint, why the human brain should be capable of understanding quantum mechanics or general relativity or the large-scale structure of the universe. These things did not matter for survival on the African plains. And yet our minds, with effort and creativity and the accumulated knowledge of generations, can reach them. The Milky Way is not just real, it is understandable. And that may be the most hopeful fact in science. Now let me ask you something about time. How long is 13 billion years, really? Not in numbers, in feeling. You've been alive for, at most, a few decades. Your grandparents might span another few decades behind you. Recorded human history stretches back perhaps 5,000 to 6,000 years. The existence of our species, Homo sapiens, goes back perhaps 300,000 years. Life on Earth has existed for approximately 3.8 billion years. The Earth itself formed 4.5 billion years ago, and the Milky Way began forming about 13.5 billion years ago. On a timeline where the Milky Way's history is compressed into a single year, the Earth doesn't form until October. Multicellular life doesn't appear until mid-November. The age of the dinosaurs spans roughly 2 weeks in December. Homo sapiens appears at approximately 11:54 p.m. on December 31st. All of recorded human history, every war, every empire, every invention, every book ever written, occupies the last 13 seconds of the year. The entire industrial age, the age of science, the age of space exploration, the last fraction of a second. We are very, very new here. The galaxy was already incomprehensibly old before the first human being looked up and wondered what the light in the sky was. And it will continue, long after the last human being does the same. This is not a sad thought, or at least it doesn't have to be. It can be a freeing one. We are young, we are new. We are at the very beginning of whatever this species might become, in whatever time remains. The galaxy has time for us, more time than we can use. Something I find beautiful about neutron stars, specifically, is how they transform the violence of death into the precision of a clock. A massive star lives a brief, brilliant life, burning hot and fast, exhausting its fuel in millions rather than billions of years. Its death is catastrophic. The supernova is one of the most energetic events in the universe. The shockwave devastates the surrounding space. And yet what remains, the neutron star, is the most orderly, most precisely measurable object we know. A city-sized ball of neutrons, spinning hundreds of times per second, emitting beams of radiation with the regularity of an atomic clock. The violence has been converted, through physics, into order. The explosion has left behind something that ticks. There's a metaphor there, if you want one. But you don't have to take it. You can simply appreciate the neutron star for what it is. An object that should not exist, that arises from destruction, that produces something useful and beautiful and precise, and that continues to tick faithfully in the dark long after everything that made it has been forgotten. The Milky Way contains hundreds of millions of stellar remnants, white dwarfs, neutron stars, and black holes, scattered throughout the disk and halo. These are the ghosts of past stars. They do not shine the way a living star shines. They do not produce new energy through fusion. They simply persist. Cooling white dwarfs radiate their stored heat into space. Neutron stars spin and pulse, and in some binary systems, accumulate material from a companion star, occasionally flaring in X-ray bursts. Stellar mass black holes. Black holes formed from the collapse of massive stars, much smaller than the supermassive central black hole, typically a few to a few dozen times the mass of the Sun, drift quietly through space, invisible unless they happen to be near enough to a companion star to draw in material and shine in X-rays. These remnants are part of the galaxy's population in enormous numbers. For every star currently burning in the Milky Way, many more have already died and left a remnant behind. We live in a galaxy whose history is written in its dead as much as in its living. Here is a fact that lives at the boundary of what we know and what we suspect. The Milky Way may have a second, hidden reservoir of baryonic matter, ordinary, visible matter, in the form of a diffuse hot gas halo extending far beyond the galactic disk. We know about the dark matter halo, which extends even further. But recent observations suggest that there may also be an enormous quantity of hot ionized gas, actual ordinary matter, made of protons and electrons, surrounding the galaxy in a spherical halo far larger than the stellar disk. This gas is too hot and too diffuse to glow in visible light, but in X-rays, it emits a faint detectable signal. If confirmed, this hot gas halo could contain as much mass as all the stars in the galaxy combined. It could be the Milky Way's missing baryons, the ordinary matter that should be present based on cosmological models, but that hasn't been accounted for in stars and gas in the disk. The galaxy, in other words, might be hiding an enormous amount of itself in a hot, invisible envelope that we are only just beginning to detect. What we see, the beautiful spiral of stars and nebulae and star clusters, might be only a fraction of the galaxy's true extent. Is there anything left? Yes, always. The universe is not a topic you can exhaust. But let me give you the last few things gently, as your breathing has probably slowed and your thoughts have probably begun to blur into the pleasant, soft noise of pre-sleep. The Milky Way is part of the Laniakea supercluster, a vast gravitational structure containing more than 100,000 galaxies, spanning approximately 520 million light-years. Laniakea is not a cluster in the traditional sense. Its galaxies are not bound by gravity the way the local group is, but they share a common region of the universe from which they are all flowing inward, pulled by the gravity of an enormous concentration of mass called the Great Attractor. The Great Attractor is itself a gravitational anomaly, a region of enhanced density pulling thousands of galaxies across hundreds of millions of light years. And the Milky Way, the local group, the Virgo cluster, all of us, are streaming toward it very slowly at hundreds of kilometers per second. We won't arrive for tens of billions of years if we ever do. The universe's expansion is pushing everything apart faster than the Great Attractor can pull us in. But the pull is there. The Milky Way is in motion not just on the scale of the galaxy, but on the scale of the supercluster. Everything is moving. Everything is being pulled by everything else, across every scale, from the subatomic to the cosmic. And yet, here you are, in the middle of all that motion, all that scale, all that ancient light and invisible matter and spinning remnants and gravitational whispers from 100 million light-years away. Here you are, still, warm, breathing, in a bed, on a planet, in a solar system, in a galaxy that has been turning for 13 billion years and will turn for billions more. You don't have to hold all of this. You don't have to understand it. You just have to be in it. And you are. You have been, every moment of your life, whether you thought about it or not. You are swimming in the Milky Way. You are made of it. And tonight, knowing just a little more of its story, you can close your eyes with the quiet certainty that you are not alone in the universe. Not just in the sense that others might be out there somewhere, but in the deeper sense that you are continuous with the universe, that the boundary between you and the cosmos is less a wall and more a membrane, that the iron in your blood and the iron in a star and the iron in the rocky skin of Mars were all made in the same process, by the same physics, in the same galaxy. You are the Milky Way, looking at itself, right now. The galaxy will still be here when you open your eyes. The stars will still be burning. The spiral arms will still be turning. Sagittarius A star will still be waiting at the center, patient and dark and 4 million times the mass of the sun. And the oldest star in the halo, the dim, orange, 13-billion-year-old survivor, will still be drifting on its long, slow orbit, carrying its ancient light patiently through the dark. As it has since nearly the beginning of everything. You are in good company. You always have been. Good night. One last thought. Just one. A small one that will fit easily behind your eyes, somewhere right now, at this very moment. As you read or listen to this, a star is being born in the Milky Way. Not in a year from now. Not in a century. Right now. In a cold molecular cloud somewhere in the disk of our galaxy, a region of gas has crossed the threshold of gravitational collapse and begun to fall inward. It will take another few million years for the process to complete, for the core to heat enough to ignite fusion and become a true star. But the process has begun. The galaxy is forming a new sun while you sleep. You will not live to see it shine. Your grandchildren's grandchildren's grandchildren will not live to see it shine, but it will shine. A new star, in the Milky Way, already in progress. And when it does, in several million years, it will add its light to the galaxy's total. It will illuminate whatever gas and dust surrounds it. It may gather planets from the remaining disk of its birth cloud. And those planets, if they form in the right positions, might one day shelter something that looks up at their night sky and sees the band of the Milky Way and wonders what it is, what it means, whether anything is out there. The galaxy will still be answering that question. It always is. Good night. And since we're here, still together in the quiet, let me give you a handful of final truths to carry into sleep like small, smooth stones in your pocket. The Milky Way has a defined edge, but it isn't sharp. There's no wall, no boundary marker, no sudden end. Instead, the density of stars simply diminishes with distance from the center, thinning from thousands per cubic light-year near the core, to dozens in the disk where we live, to single isolated stars separated by tens of light-years in the outer halo. To nothing. The galaxy fades rather than ends. Its stars become sparser and its influence becomes weaker until the gravity of the intergalactic medium takes over. There are stars that may be gravitationally bound to the Milky Way hundreds of thousands of light-years from the center, far beyond what we normally consider the galaxy's disk. The edge of the Milky Way is wherever its gravity last has a claim, and that turns out to be very, very far indeed. The Milky Way travels through space as part of the local group, which itself moves through space relative to the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe uniformly. We are moving at roughly 600 kilometers per second, relative to this background. Not the solar system's orbit around the galactic center, not the galaxy's orbit within the local group. The entire local group, the Milky Way, Andromeda, all 50-plus member galaxies, hurtling together through the cosmic background at 600 kilometers per second, in the direction of the Centaurus constellation, toward the Great Attractor. Pulled by gravity we can feel but not fully see. We are travelers at every scale. There is no frame of reference in the universe that is truly, absolutely still. Motion is the default state of everything. Some of the hydrogen atoms in your body were formed in the first 3 minutes after the Big Bang. Not the carbon, not the iron, not the calcium, those came later, forged in stars. But the hydrogen, the most common element in your body, in water, in the organic molecules of your cells, that hydrogen is original, primordial. It formed in the first few minutes of the universe's existence when conditions were hot and dense enough for protons to stick to each other and form atomic nuclei. That hydrogen eventually became part of gas clouds, then stars, then stellar remnants, then new stars, then the solar nebula, then the ocean, then rain, then rivers, then food, then you. The hydrogen in you has been on a 13 billion-year journey. And tonight it is here, resting in a bed, at the end of a long day, waiting to continue the Milky Way hums. Not audibly. Sound does not travel through the near vacuum of space, but in the radio frequencies that radio telescopes detect, and in the low-frequency gravitational waves that wash through the universe from the mergers of supermassive black holes, the galaxy ends resonate. Pulsars tick. Hydrogen clouds emit their characteristic 21-centimeter radio wavelength signal. Supernova remnants glow in synchrotron radiation from electrons spiraling in magnetic fields. The hot coronal gas emits X-rays. The cold dust emits infrared. The galaxy is broadcasting, constantly, in a dozen frequencies simultaneously. We live in the middle of a vast, complex, multispectral signal. We are bathed in it. We just can't hear it. There are stars in the Milky Way that will still be burning long after the sun has died. The smallest stars, red dwarfs, burn their hydrogen so slowly and so efficiently that they can live for trillions of years. Some red dwarfs formed early in the galaxy's history will still be fusing hydrogen when the universe is 100 times older than it is today, when every star like the sun has long since become a white dwarf, when star formation has stopped across most of the galaxy, when the night sky, from any hypothetical surviving planet, is far darker and emptier than the one you'd see tonight. Those small, patient red stars will still be burning, outlasting everything, carrying the Milky Way's light far into a future we cannot imagine. You are alive in the galaxy's middle age, when it still has stars like the sun, still has molecular clouds, still has star-forming regions lighting up the spiral arms, when the sky is rich enough to be beautiful, but orderly enough to be readable, when there are enough stars to inspire wonder and enough dark between them to inspire humility. You are alive at the right time, in the right galaxy, in the right arm, in the right quiet spur, at the right distance from the center, on the right kind of planet, orbiting the right kind of star. And you are here, alive, aware, wondering, against odds so enormous that the universe itself would be forgiven for not expecting it sleeps now. The galaxy will carry you through the night,